I've spoken at, I don't know, half a dozen different Spark summits, and the audience keeps getting better. I like coming to Europe a lot. In the US, the hallways are full of people. In Europe, the conference halls are full of people. And you guys ask harder questions, so I actually love it. My name is Simeonov. I'm the founder and CEO of a company called SWOOP. Business kind of runs on Spark. We do a lot of big data processing, machine learning, and AI. And we have tons of data, petabytes of it. Our own data we've collected through various activities, de-identified data on 300 million patients, HIPAA safe. HIPAA is the Health Information Accountability and Portability Act. Think of it as GDPR compliant data. We also have a lot of privacy safe consumer data. And we use this information to figure out how to help patients. We can figure out people who have undiagnosed diseases, take intervention, improve outcomes, save lives. And it involves a lot of data crunching. A lot of it's machine learning and AI, but some of it is just analytics. People care about counts of various things. How many patients of this and that type. We don't care who the patients are. We just want to know that they exist. We've been involved in the open source community with Spark. We've released a few libraries. If you are dealing with any type of data ingestion of untrusted data in strange formats, especially coming from the outside world, Spark Records will probably make sense for you. It's a system that allows you to handle all kinds of problems without stopping your jobs, and essentially attaches a structured row-level log file to your data, so you can actually query any errors or warnings or debug issues or quality issues that happen when you ingest your data in Spark. You can, for example, when something goes bad in production, you could run a query to say, just give me the top 3 exceptions that have happened in the last hour, sorted by how frequently they happened, and give me the first line in the stack trace of the exception where my company name, in this case, com.swoop on a package is mentioned, because if you see none.get or null pointer reference, that doesn't really help you do root cause analysis, and you kind of want to know, great, but what part of my code did that? We also open sourced call it a bag of tricks, which is spark-alchemy. The name comes from alchemy, it's magic, and it makes our data engineers and our data scientists look like magicians because they're so productive. And today I'm going to talk about one aspect of spark-alchemy, particularly a release that just happened yesterday, that improves performance and interoperability when it comes to doing high-performance analytics. Analytics is basically about counting things, and there's only one rule about how you make analytics jobs run faster. It is to process fewer rows. No other strategy is guaranteed to work. And you can do fancy things in how you process rows, but fundamentally, if I process 1,000 times fewer rows than you do, I'm going to run a lot faster than you. I want to try to convince you today that the most important property of a high-performance analytics system is the reaggregability of its data. What the hell does reaggregability mean? Well, aggregatable is a word, but reaggregatable is not. And aggregatability is a word, so I decided I'm going to invent reaggregatability. It's basically a property of data that allows it to be reaggregated. What does that mean? It means that you can sort of aggregate it once and then reaggregate it, or pre-aggregate and then reaggregate. Well, what does that mean? Well, before we get there, let's talk about the problem. The problem here is count distinct. Anytime you have count distinct in an analytics system, you got a problem. And the reason is because count distinct is not reaggregatable. Most other things are. So here's an example of reaggregability, right? Let's say you're summing the number of times something happened, right? Well, maybe you count them. That's initial aggregation. But counts can be reaggregated by summing. Mins can be reaggregated with min because the minimum of a bunch of minimums is the minimum of all of them. Same with maxes. But the odd one out is count distinct. If you have a website and you have 5 unique visitors yesterday and 5 unique visitors today, the number of unique visitors for the 2 days may be any number between 5 and 10. Right? So the problem with count distinct is that to answer any query with count distinct, you have to process all original rows of data. So that's why count distinct is the bane of analytics systems. Because if the only way you can have a high-performance analytics system is to process fewer rows of data, then you want to be able to aggregate and reaggregate. Shrink the number of rows you're working with. But you can't do this if you need to produce distinct counts. And we always want to produce distinct counts. Well, maybe anybody in data engineering never wants to produce distinct counts, but business people always want distinct counts. Number of sessions, number of unique users, number of patients, number of doctors in our world, and so on and so forth. So we have to deal with this problem. It's a very fundamental problem, right? Mathematically, count distinct is not reaggregatable, so what do we do? So to make things more concrete, I decided to pull some sample data, run queries a few times, and we're going to report sort of median statistics so we can see the nature of the problem. So I pulled the prescriptions, the prescriptions that doctors give patients for 2018. It's about 10.7 billion rows of data, narrow table. Normally, again, it's a toy example. Normally, our tables are super wide, hundreds of columns. In this case, I just pulled a handful. The date, the generic drug name, the branded drug name, the product, which in this case is a code for the specific drug. In the US, each one has a numeric code. There's over 1 million of them. And then the patient ID and the doctor ID. Kind of really, really basic data system. It's not very big, only about 150 gigabytes. And so we did a test with a Spark cluster where in expanded form it can all fit in RAM, because we don't want to be comparing I/O performance in the cloud. We just want to be performing kind of core ability of Spark to process data. And Spark here is not unique. Pretty much any distributed computation system, BigQuery, Presto, et cetera, is going to have the same performance characteristics over this type of data. So we're talking about a very, very fundamental problem, and one that many other systems can't solve because they don't have the extensibility that Spark has. So here's what the data looks like. They're fairly short strings, and there's a few longs. Nothing really special about it. So you can imagine it's any type of data, right, that we need to crunch and build an analytics system with. The fact that it has to do anything with health for patients here is irrelevant. It's just simply the data that I have easy access to. So let's do a basic query, right? Let's just see, business people often want to get information by month, because that's kind of the cycle of business life very often, bigger decisions. So let's just get, the distinct numbers of prescriptions, the number of prescriptions, and then the distinct number of generic names and brand names per month. Really basic stuff, runs for a few minutes. You see, the input is not that big, only about 10 gig from the 150, and, fairly small shuffle, not much memory getting exchanged, because there are not that many generic drug names and there are not that many branded drug names. They're just, in the few thousand to 20,000 range. So count distinct essentially needs to count for each unique value. And if there are only about 20,000 short strings, you just don't need to move that much data. But you need to go through 10.7 billion rows, and that takes some time. So using this basic idea that the only way you have high-performance analytics is by reducing the number of rows you process, we can ask the basic question, what can we sort of pre-aggregate the data somehow, and then rather than going through 10.7 billion rows, only go through the rows of pre-aggregated data. And in this case, obviously, there's a really simple thing we can do. If we commonly ask for the data by month, we can aggregate the values by month, doing essentially dimensionality reduction of the date column. So we do toDate and truncate the date to month, keeping generic and brand for this particular query, right? Because we want distinct counts on those, so we can't really reduce them in any way. But of course, the number of scripts is just a normal count, and that reaggregates. So we do this once, and then, we run 50 times faster. Right? Instead of going to 10.7 billion rows, we go to the pre-aggregated table. You know, this is sort of molecule and apple pie in high-performance analytics, and how you try to beat this problem of reading every row. But keep in mind, again, anything we're doing count distincts on, we kept every unique value of. Right? We couldn't do any dimensionality reduction on those. And you can see how the shuffle, although it's still there, shrunk in number of rows and shrank by a factor of 10, from a gigabyte to 100 megabytes. By the way, we're only 50 times faster because out of the several seconds that it took, half the time is Spark sort of starting things and ending things, because Spark is not a sort of high-performance simultaneous query type database, and you know, Spark job has a meaningful startup cost. If you just compare how many fewer rows we are processing, by running a simple query, we're processing 4,000 times fewer rows. So if the data were actually bigger, or the Spark didn't have such a high startup cost, we'd be running closer to maybe, you know, hundreds of times or 1,000 times faster. You would be if you were using something like Postgres, for example. But we have a problem. This type of trick only works if you have low cardinality dimensions. Cardinality is the number of things in a set. So basically, it's the number of distinct values in a dimension. Right? Generic names and branded drug names, thousands to tens of thousands, right? Easy stuff. But about 350,000 drug codes has about 4-point-some-odd million doctors and nurses and other health professionals in the US, and there's about, in our data, 300+ million patients. So if you wanted to do this trick with, say, patients or doctors, you wouldn't be reducing input rows by a factor of 4,000. You'll maybe get lucky and reduce them by a factor of 30 by going from days to months. But maybe not, because not every patient goes to the doctor every month. So realistically, you reduce it by a factor of 2, 3, 4, and that's just not good enough. The other problem is that in addition to the size of input, we also have to worry about the size of shuffle, right? Part of the reason why the first job ran in only several minutes was because the shuffle was fairly small, because we were shuffling low cardinality dimensions. But if you need to shuffle 350 million distinct things to every core in your cluster, potentially, then you're talking about a very, very large shuffle, which is going to be very, very slow, especially in the cloud, where the dirty little secret is that I/O is terrible. So let's see what happens, right? Let's just throw in a distinct patient count in there. And suddenly, we are more than 2 times slower. And check what happened to our shuffle size. From 10 gigabytes, it's now 100 gigabytes. The shuffle size went by a factor of 10, which means that I/O went by a factor of 10. And keep in mind, that isn't just sucking in I/O from a place where you can get it into a node. That's nodes talking to each other. So it's in and out. So you're saturating network interfaces and cloud and so on and so forth, and you basically just have CPUs kind of twiddling their thumbs waiting for data. That's not good. So some of you may know that Spark has approximate distinct counting functions. And you kind of go, wow, you know, those things count faster. Maybe we should try them. So there they are. We've replaced the count distinct with approximate count distinct. We're using the default 5% error that Spark has, which I'd argue is too large for many business cases. You know, we typically write to run with 1% or lower error in our cases when we use them. And, you know, we get some benefit. You know, we run about 3 times faster. The shuffle is more than 10 times smaller. So clearly something very nice is happening with approximate distinct count, but 3 times faster is not good enough. And the problem that we're only 3 times faster is that we're still processing every row of data. Basically, the only thing that approximate count distinct, the way it's implemented in Spark, gives you is smaller shuffle. But still touching 10.7 billion rows. I don't know about you, but fundamental problems in big systems don't get solved by 2 or 3x performance improvement. They need sort of 10 to 100x performance improvement. So that's not good enough. Part of the reason is that the people who implemented approximate count distinct in Spark, they were good engineers and understood the HyperLogLog algorithm behind it. They fundamentally had no idea how actually HyperLogLog is used in big data systems. Folks at Google have an idea, and so BigQuery has had a very different kind of support for HyperLogLog for years. And what type of support, we'll learn about it later, and we'll learn how to use it in Spark. So we have this basic question, like we want to do approximate distinct counts. Clearly it is a much smaller shuffle. We just cannot have this problem of going to every row of data. We need some way to be able to pre-aggregate. And yes, we can do it. The basic idea is that under the covers, HyperLogLog approximate distinct counting happens in these 3 steps internally. Right? On each of the workers, this thing called a HyperLogLog sketch, which is a binary data structure, gets created. Those are the things that get shuffled between the workers, and they are the things that are many, many, many times smaller. And then, out of those things, once they get merged and unioned, you can sort of say, hey, what's the approximate distinct count of things? So this binary data structure, the HyperLogLog sketch, it's difficult to describe what's in it. Basically, what's in it is the ability to compute an approximate distinct count. There's a bunch of math behind it, which I have a few links, those of you interested can take a look at. But fundamentally, that's what it's about. Right? It's kind of difficult to describe exactly what's in the data structure, short of things that allow you to compute distinct counts. That's what it exists for. And if that's how HyperLogLog works under the covers, then maybe we can just kind of split it up and say, hey, these sketches that you build, now you kind of build them on the worker, shuffle them, and use them to compute counts in one shot, having looked at every single row of data. But what if we just persist them in a binary column? They're clearly reaggregatable because you can merge them to create another HyperLogLog sketch. So that's our pre-aggregation step, right? And then our reaggregation step simply is merge whoever you need to merge from the HyperLogLog sketches you've already built. And then when you're ready to actually present a number to humans, ask the sketch, how many things are you actually representing? Right? So now suddenly, distinct counts, well, approximate ones, fall into the pattern with normal counts and with mins and the maxes and collect lists and collect sets and array unions and all these other things that you may want to do in a high-performance analytics system. Now we suddenly have an architecturally consistent world. And we have a way to not touch every single row of input data. And that completely changes the game. Beyond just what you can do with Spark, which we'll talk more later in the talk. So spark-alchemy as a library, the release just went out yesterday with some additional capabilities in our HyperLogLog support, including interoperability, conversions between different formats, and so on and so forth. So normally you're not supposed to be on your phones in sessions. Get on your phones, enter the link, sign up to get releases. This is really good stuff. If you have to do any type of analytic work, this is something you should be playing with and experimenting and probably adopting. So what does pre-aggregation with HyperLogLog sketches look like in Spark with spark-alchemy? Well, you just have this function called HLL init agg, which basically means build me a HyperLogLog sketch for whatever value is in a single row, and then whatever you're grouping by, just merge them all together. Or a way to think of it is a two-step operation. One is HLL init for every row, and then an aggregate function like sum, which is HLL merge, which says kind of combine them all together, right? And we put patient IDs in this. We keep everything else the same. Generics and brands still, we're going to do precise counts, still truncating dates to month. Now if we run the query, it runs basically at the same speed than a query without patient counts, because we are again reducing the data input by about a factor of 4,000. And again, the real speed is much, much faster net of Spark startup time. And the way we do it basically is, this is the merge portion, right? This is the aggregate function that merges the HyperLogLogs to the level you want to present to a human. And HLL cardinality is the piece which says, okay, turn this binary data into a number. And here, just for comparison, I'm still using the 5% error. Obviously, if you want to reduce the error, you use slightly bigger sketches, you use a little bit more space, and we'll talk about the trade-offs a little bit later. But it's fundamentally not impactful when you compare it to a 4,000-fold reduction in input. Meaning, you can actually compute at very, very low errors, even though it's not precisely accurate. What I want to do now is kind of, without going into the math of it, and again, there are links, there's tons of information on the internet if you guys are really curious about the math, and the math is really fun. But I want to give you the intuition of how this actually works, because there's a number of other probabilistic data structures that can be used in similar ways in extensible systems such as Spark. You can't think of using them in Oracle or another database which is closed, right? Or it would be a real pain in the neck, like you have to write a native Postgres extension and so on and so forth, like the Postgres support for HyperLogLog. But in Spark, it's just a lot easier to add these types of capabilities. And so if you're crunching a lot of data, if you worry about the performance of analytic loads or featurization for ML, et cetera, investigating probabilistic data structures is actually really important, because it's not that difficult to add support for them in Spark. So imagine you had n items that you're going to randomly distribute in k buckets. So if you do that, on average you'll find that the distance between each of the items will be roughly the number of buckets divided by the number of items. Obviously here we're assuming that the number of buckets is not very similar to the number of items, because you're going to jam everything full, but even then, distance will be about 1, right? And by the same argument, that's also the distance from kind of the beginning of your buckets to the very first item where it lands, right? That's on average. Which of course means that you can then estimate the number of items from the number of buckets and essentially the position of just the very first item. Oh, by the way, the very last item. Doesn't matter. And what this means is that, whoops, what happened here? My machine decided that I'm not using it and fell asleep, even though I turned on whatever you need to tell Mac that, no, I'm actually using you, please. So you can forget about all these things, and if you remember just this one, and not even the item itself, just its bucket number, you can actually estimate the number of things that you put in the buckets. That's pretty cool. Rather than remembering n things, we need to remember just one thing. Now, obviously, if we just do this with one set of buckets, we're going to have huge error. Well, the way we deal with problems with huge error is we like to get a distribution of them, and then we like to compute a statistics on it, like, say, the mean or the median. Right? And by the way, the other way to lower the error is you can have more buckets. Because the more kind of space we have, the more precision we have. It's kind of like your resolution. Back to the distribution. So here, if you had a number of sets of buckets, and we drop the same number of items in them, and we just look at the means. The means are the blue. The minimums, they're the blue. And the true mean is 5. So you can see that some of them fall on one side and some of them fall on the other. That's our distribution. Right? So if we just keep a number of mins from kind of different sets of buckets, we can then compute their mean or median or some other statistics and get a much more accurate estimate that allows us to then get to the number of items. Does that make sense? I'm taking poetic license here. This is intuition. This isn't actually the details of how it works because the algorithms are very, very highly optimized, use very little space. And we'll talk about some of these details. So the fundamental insight here is that HyperLogLog sketches are reaggregatable because they're based on mins or maxes, and maxes reaggregate with mins or maxes. Right? And because we just care about mins and maxes, we can forget about most of the data. But of course, we need more than one min or max. We need some number, but we need a constant number of mins or maxes, right? To sample. And then if we want to get more resolution, more precision, we can also ask for more buckets. But again, we can ask for a constant number of buckets and improve our resolution kind of regardless of the number of items we're counting. And that's really good, because we can get reaggregability in effectively constant space, or in space which, practically speaking, grows, logarithmically or double logarithmically relative to input data. And it was just intuition. In the real world, things get complicated. I said that we're uniformly distributing items in buckets. Data in the real world is not uniformly distributed, pretty much ever. But there's the hashing trick. You make data uniformly distributed by basically hashing it. And in Spark, you can hash anything. You probably don't want to use Spark's own hash function because that's 32-bit murmur-free. You probably want to use a 64-bit XX864. But the insight's the same, right? We have a very easy hack for turning non-uniformly distributed data into uniformly distributed data. We just hash it. One of the problems with building distributions of hash things is that it's actually very, very difficult to find families of hash functions that are independent of each other. Right? If we're building a distribution of things, we don't want them to be correlated. Right? We don't want them to all not really be randomly distributed around the true mean. So the solution for that is, rather than actually figuring out, based on whatever data we're using and whatever implementation we're using, how to come up with these magical independent families of hash functions, which mathematicians tell us is really difficult to do, we can instead partition our data. Right? It's a zero-knowledge strategy that will work most of the time. You say, hey, I'm just going to take a chunk of the data here, chunk of the data again. Not exactly how it works in practice, but that's the core intuition. There's still some problems at the edges of very few things, too many things given the buckets, but with a bit of math and with some numerical estimation, just by running a whole bunch of different tests, which folks like Google have done at significant expense, you can actually come up with corrections at the edges to get quite accurate means for very, very wide ranges of data. And that's some of the difference between when you hear HyperLogLog and HyperLogLog++. The plus plus part are the Google tweaks based on a bit of extra math, a bit of extra data, and a whole bunch of sort of empirical experiments to know how to tweak things to make things better. And actually, we don't even have to keep the minimums, because you can think of minimums as numbers. There's some very interesting property about the distribution of bits in random integers. It turns out that you only need to keep, for example, how many zeros until the first one in the binary representation of the hash value. So we don't even have to keep an entire minimum of whatever it is, 64 bits. We only have to keep a number, say between 0 and 63, which is where does the first one appear in the hash value. So we're really jamming things down and effectively not losing any precision, keeping the same insight that mins reaggregate with mins, and just a minimum allows you to estimate the number of things. This is really neat. The typical objection you get anytime you introduce the notion of approximate counting is, but we have to be precise. It is a business imperative. That is bullshit. Most things in business are incorrectly measured. I mean, there's some exceptions in highly transactional, super reliable systems, but most data that business decisions are made on is by its input approximate. So precisely counting imprecise things gives you absolutely no guarantee that you're producing a better result than counting the same things with a small error of, say, 1% or 0.5%. Absolutely none. A lot of business people want to understand that, but that's the reality. And it leads to hundreds of times faster processing. So when you turn it into a cost-benefit issue, the issue typically goes away. You can trade off the size of sketches with the error you get. This is a table from BigQuery's HyperLogLog functions from Google. The value on the precision column is how many bits you're using, and that's kind of a tuning property of some HyperLogLog implementations. Others tune based on error, which is what Spark does in approximate count distinct. This is sort of Google's implementation of the maximum sketch size. Other implementations are more or less, a constant factor of 2 around the same thing. And these are the errors you get. Now, CI stands for confidence interval. I'll think of it as standard deviations from the mean of a normal distribution, or Gaussian, as some people call it. So in other words, so one standard deviation from the mean of a normal distribution covers 65% of the values. When you do approximate count distinct in Spark or in spark-alchemy, and you put in 5%, what you're basically saying is, I want an approximate distinct count that at 65% confidence interval, one standard deviation away, is statistically guaranteed to be less than or equal to the value that I provide. And of course, if you want it to be 95+% confidence, then you got to go 2 standard deviation, just half the number. Right? If you want to be 99+% confident, just half the number again. So it gives you a very, very simple way to decide how you want to tune your counting. And you can see that the rough intuition is that to have your error, like to go from 0.4 to 0.2, you increase your size of sketch by a factor of 2. So basically, the data grows quadratically with error reduction, which is not that bad. Keep in mind, we have to do this once, but then we can reaggregate many times. There's some articles about HyperLogLog that compare approximate distinct counting in this sort of one-shot approach and say, be careful. If you choose a low error, it will actually be slower than a precise distinct count. Yeah, but that's besides the point. Approximate distinct count reading every single row of input data is kind of silly. It just gets you, a few times faster performance. It doesn't solve any real problems. It doesn't matter if your pre-aggregation step runs 5 times slower than your precise count distinct, because you're going to do it once. And then you're going to run tens to hundreds to some cases thousands of times faster for every single query. So you can actually build a Approximate count whose error is, a fraction of 1%, and still be running more than 10 times faster in a final queries, which is a very big deal. At this point, the argument about precision really kind of flies away. The other interesting point here is about interoperability, right? With Spark, thinking of it as a unified data platform, you can move all kinds of data between different systems, JDBC, flat file formats, modern file formats, the connectors to Mongo, the connectors to BigQuery, the connectors to Redshift. And you can do this for your counts, even for arrays in some cases, but not for HyperLogLog. Well, we want to change this with spark-alchemy because we think it's really important for data to be interoperable across systems. Think of it this way, right? It used to be that whichever system produced the final query for a user, it had to be the system that had all the raw data. Because if you have a single, well, if you expected to have a single count distinct calculation that mattered, you couldn't do it on any pre-aggregates. So there you are maintaining a large relational database with big data volumes. It's really expensive. But if you could pre-aggregate in Spark, and let's say push to BigQuery or push to Postgres or push to Redshift, you can have a system where the heavy lifting and the big data management is managed on low-cost storage with low-cost cloud compute to reduce the data substantially, and then you move a tiny fraction of the data over to a system that's very good at interactive queries that you can run at a hundredth of the cost of what you would need to run and maintain an available cluster for queries arriving at random times with the full raw data. Not to mention all the ETL issues you're going to face along the way. So we currently support two different formats. One is, they're both open source libraries. We just integrated them into Spark. One is from Streamlib, which got acquired by a company called AddThis. I don't know them interoperating with anybody else. The other one is from a company called Aggregate Knowledge, which got acquired by Newstar. They actually published a storage specification for their HyperLogLog binary data structures. And so the native Postgres HyperLogLog extensions is based on that storage format. So if you build your HyperLogLog sketches in this format using spark-alchemy, you can actually load them into Postgres. You can load them into Citus. Those extensions are supported by default, for example, on AWS's RDS. You don't even need to install them. They're there. BigQuery published its own HyperLogLog sketch format in July. It's a really cool open source project where Google sort of opened their HyperLogLog implementation. It's called ZetaSketch. But it's kept kind of hush-hush because Google doesn't really want people to move their data out of BigQuery. They'd much rather have it be locked in. But of course, we don't want it to be locked in any one system. We want it to be able to move. So I'd love to see a PR to spark-alchemy with somebody who provides ZetaSketch support. In fact, I'd love Spark itself to actually create the capability to persist the internal sketches that get built into binary columns. Again, the function you'd use in spark-alchemy to convert from one type to another is HLL-convert. You cannot go from every type to every other type because there's some issues. You can go from HyperLogLog ++ to HyperLogLog, but not the other way around. But again, those are relatively sort of simple mathematical limitations. You can do it in most cases. There are other benefits to HyperLogLog sketches. We talked about the high-performance analytics thing. Privacy is actually a really huge benefit of using HyperLogLog, and privacy is very important. Funnily enough for Americans to say that, because in Europe the assumption is that nobody in America cares about privacy. But at the Spark Summit in London, I was actually giving a talk on privacy and privacy-preserving ML and AI models. Most people do care about privacy. It's just that some companies prefer to make money not caring about it. You can do unions across columns. You can also do intersections with bigger error. So my call to action for you today is pretty simple. Check spark-alchemy out. Learn about probabilistic data structures if you're managing large amounts of data, because beyond HyperLogLog, there are other cool ones, and there are open source libraries that you can integrate into Spark using the ideas that spark-alchemy has done. And that is all. Thank you so much for coming today. I'd love some questions.
Thank you, Sim, for the talk. And yeah, let's take one question.
And I'll be here after anybody can come. We'll walk out in the hallway. We can chat.
So thank you for your great talk, first of all. So in my company, we are working on the same problematics. We are especially working on Cheetah Sketch for some restriction about the intersection and exclusion sets operations. So is why we choose this data structure. But we have some latency issues where we have cardinality not in the IDs we want to sketch, but in dimensions. So my question is, there is some design we can apply on data to handle this kind of bottlenecks on...
The short answer is it depends, because most of optimization strategies, when you think about dimensionality reduction, are very data type and data property specific. Right? HyperLogLog isn't about dimensionality reduction. HyperLogLog is about measure computation reduction. Right? So if you want to slice and dice or group by very precise values, right, or filter by precise values, HyperLogLog won't help. The moment you hash things into a HyperLogLog sketch, you lose track of what they are. So you can't just say, oh, only filter by blah. What you have to do if you have conditions is actually either put them as actual dimensions, so you end up with more rows, or you do a cross product of your sketch with your condition and you generate multiple columns, right? So that would be the approach.
Yeah, I see. Thank you.
Thank you for your talk, Sim, and we can take more questions.
I'll be here and then I'll
offline.
step out. Thank you.